Okay, so in this video we're going to talk about representations of functions as power series. So basically, instead of having something in a nice function notation, we're going to write things as power series. And you might think, why would we want to write something as like this when we could write it as a function? Well, first of all, not everything can be written as a nice function, and some of the most important functions in like the sciences, such as Bessel functions, are actually defined by power series and can't be expressed in terms of elementary functions. Basically, the Bessel functions and other functions that really can't be expressed in terms of elementary functions come about through the derivative or the integral of power series. So yeah, basically we can't write them as an elementary function. First of all, that's one reason why we want to do this. But even functions that we can write as an elementary function doesn't necessarily have some simple integral to integrate it with. Like we can derive most anything, but integrating things, sometimes we run into issues. So even if we can write some function, we might not necessarily know how to integrate it without converting it into a power series. And essentially, the idea here is we can write our function as a power series, integrate it, and that power series is functionally a polynomial. And when you integrate a polynomial, we get another polynomial. And so even if we're using it as approximation, we're basically using polynomials to approximate our functions, which, if you recall, is very similar to our Simpson's rule. And this is used in the sciences as well to simplify expressions being dealt with. So if we don't want to deal with something more complex, and we really don't have to, because oftentimes in the sciences, right, we're dealing with things that are only to a certain significant figure. So if it's accurate enough, then it's accurate enough. There's no need to be any more accurate. So that's one reason to do it. It's also used in kind of computer science to evaluate functions on calculators and computers, because essentially that's easier for it because it turns it into a series that then does partial sums, which are easy enough for a computer to do. Okay, so let's now talk about the method. So essentially, the idea here is that we want to recall our geometric series, because the geometric series is what we're going to use to write our functions as power series. So if you recall, the sum as n equals 0 to infinity of a r to the n is equal to a times 1 over 1 minus r. This is the series of a geometric. So if we want to find this, it's a times 1 over 1 minus r. And as a reminder, that really just comes from our partial sum. S sub n is equal to a times 1 minus r to the n over 1 minus r. And we take the limit as n approaches infinity of this thing. And as long as r is less than 1, then r to the infinity would go to 0. So 1 minus 0 would just be 1, 1 minus r. So that's, again, our the geometric series. Okay, so knowing that, basically, if we want to write something like 1 over 1 minus x as a series, well, that is just going to be 1 plus x squared plus x cubed. Now, let's think about that, why that is, okay? So let's think in terms of this r here. Let's call r some r less than 1. So let's say it's 1/2. A geometric series then. And we're going to assume that a is 1. Okay, just to make our lives easy. That's this assumption here. Okay, so assuming that a is 1, and let's call r 1/2. Okay, so we would have the sum n equals 0 to infinity of 1/2 to the n. Okay, let's think about what that is. When n is 0, this is 1, plus when n is 1, this would be 1/2, plus when n is 2, we would have 1/2 squared, plus 1/2 cubed, and so on and so forth. Okay, now we're going to replace this r, instead of with a particular number, we're going to call it x. Okay, so I mean, it's a real simple conversion, right? R is just some ratio. We're now going to call our ratio x. So by that same logic, our first term in our series would be, so if we're thinking x to the n, because that's what this thing is here, when n is 0, that's 1. When n is 1, it's x. When n is 2, it's x squared, and so on and so forth. So basically, we can write this exponential here, x to the n, as a series. Again, off of our geometric series. But this requires that our absolute value of x is less than 1 because x is literally the ratio, our common ratio. Or not, yeah, our common ratio in our geometric series, okay? So we're going to use this basic logic. That is, this thing is equal to this, okay? Where we are going to try and match all of our functions into this form, 1 over 1 minus something. And that something is going to be raised to the n. So if we have something 1 over 1 minus anything, doesn't matter what that anything is, this will be the sum, n equals 0 to infinity, of that anything to the n, so long as the absolute value of anything is less than 1, whatever that anything is. Again, anything we want it to be. If we can force our function into this form, then we can write it as a sum. Is that easy? But, well, it's easier said than done sometimes. Okay, so basically, we say that this sum, x to the n, with x less than 1, is a power series representation of the function 1 over 1 minus x on the interval from -1 to 1. This is because the interval -1 to 1, we're talking about in terms of x. X is between 1 and -1, okay? Because if we solve this absolute value inequality, if you recall, we drop the inequality and we write this, but then we also flip it. X is greater than -1. So that's why it's in between -1 and 1. Okay. So this power series can be used to obtain power series representations of many other functions. Again, the idea is we're just going to try and write our functions in that form. Now, basically, because the sum of a series is a limit of the sequence of partial sums, that is to say, the limit as n approaches infinity of our partial sums, we can actually then just use partial sums to approximate our functions. So let's say we can't find what the integral of a function is. Well, that's not really that big of a deal because we can do the integral of a partial sum because it's pretty easy to integrate a polynomial because we can just do individual terms. We integrate that thing and we just do it as far as we need to, basically, okay? So essentially, if we look at this red function here, this red function line is our function, 1 over 1 minus x. And so our partial sums, as we take this out further and further, they get better and better approximations. And we can actually see that on Desmos maybe a little bit better than this function. So 1 over 1 minus x is our function. Now, we're looking only at -1 to 1. So let's go ahead and define that. F of x is equal to squiggly brackets, -1 less than x less than 1. Okay, so really we're only looking here. That's what it's telling us, is that this is true around this region. And so our sum is only true on that interval. Now you might say, oh, that seems really restrictive, but the reality is that it's kind of like around this interval around kind of like a center point. So in our case, our center here is 0. And so essentially, we can move that if we need to as well. So it's not that restrictive. Okay, so let's think about the partial sum. 1 over 1 minus x, or in this case, our sum, n equals 0 to infinity of x to the n, because these two things we're saying are the same. All right, so let's think about our first term. When n is 0, we'd get 1. Plus our next term, when n is 1, we'd get x. X squared, x cubed, x to the 4th, so on and so forth. So let's go ahead and take a look. Now, 1, f of x equals 1, is clearly not a very good approximation. But, so the first partial sum, not so much. But the second, that's a little bit better. Okay, the third, that's looking a lot better, right? So the fourth partial sum, that's better. I'm sorry, should have been 3. I said 4 out loud, so there we go. The fifth partial sum would be x to the 5th here. Okay, so adding x to the 6th plus x to the 7th, and so on. And you see that this is starting to better match our red function. And basically, as n goes to infinity, this just gets better and better and better as an approximation. So that's what we're doing here. Now, let's go ahead and see this in action. Again, the reason why we're doing this partial sum is, what if we can't really find the limit as n approaches infinity? Like, what if we can't find it as n approaches infinity? That's okay. Partial sums, as you know, are good approximators, or as good of approximators as we need them to be, depending on how far out we drag the n. Okay. So let's talk about finding a power series representation of this function, and we're going to determine its interval of convergence. So that's another thing is, again, I talked about this interval here from -1 to 1. Basically, that interval of convergence is where our function is, our function and our sum are the same. So it only applies when x is between this interval of convergence, which we say from -1 to 1 in our previous one. Okay, so find a power series representation of this function and determine the interval of convergence. So what we're going to do here is we're going to try and match this to 1 over 1 minus something, because this thing is our sum as n equals 0 to infinity of that something to the n. So that's what we're trying to do. The 1 minus, we need it 1, we need a 1 minus, and then we need something. So in this case, our something is just x squared. So this will be the sum, n equals 0 to infinity, of x squared to the n. Okay, so let's think about what that is. That's the sum as n equals 0 to infinity of x to the 2n. Now, you might say, how do I know that this is true? Well, let's take a look at what this thing is. So as when n is 0, that would be 1, plus when n is 1, that would be x squared, plus when n is 2, it'd be x to the 4th, x to the 6th, and so on and so forth. Okay, now we're going to see, is this a good approximator? But first, we need to determine the interval of convergence. So if you recall, the ratio has to be, the absolute value of our ratio has to be less than 1. That's our geometric series, and our ratio is this thing inside the parentheses. So that is to say, whatever's inside the parentheses has to be, absolute value has to be less than 1. So we are saying then that x squared absolute value is less than 1. Okay, so that is to say x squared is less than 1. So x squared is less than 1 and greater than -1. Okay. Now, realistically speaking, x squared will always be greater than -1. I mean, that makes sense, right? But we're still going to be looking at this interval here from x squared less than 1, less than -1. One of the things that we can actually do, if we want, is take the square root at this stage. So let's take a look at it. So if we take the square root and solve for x here, okay, square root of the absolute value of x squared, square root here, we get absolute value of x is less than 1, which means x -1 and 1. Okay, and again, I mean, if we take the square roots plus or minus, technically speaking, but there's our minus, it's taken care of here. Okay, but well, whatever. So we have this thing, when is it less than 1? And if you're not sure about your inequalities, I mean, we can always pull up Desmos and double check these things as well. So like, when is the absolute value of x squared going to be less than 1? Okay, it's in between -1 and 1. Again, what we expect. Okay. All right. So obviously, we need to remember our inequalities from college algebra and intermediate algebra, I suppose. But basically, the idea is, yeah, we're going to now look at this interval of convergence. This is our interval of convergence. It's from -1 to 1. Now, you might say, why aren't we checking the endpoints like we did in our previous sections with the ratio test? And the reason why is because our ratio in a geometric series has to be strictly less than 1. Otherwise, the series diverges. If it's equal to 1, it diverges. So we don't have to check those endpoints because we know when it's equal to 1, it diverges in a geometric series. So it's always this open interval here. Okay, so let's go ahead and take a look and see, is this thing around our same interval, is our series going to be similar to this function? Again, looking from -1 to 1. Because that's what we're saying, is that this thing is that as n goes on to infinity. So let's take a look at it. 1 plus x squared plus x to the 4th. I mean, that's looking pretty good already. I think that's pretty believable. Okay, so yeah, that seems to check out. This looks like it is equal to that statement. So that's one of the ways that we can check this, is just take a look at your series and take it out a little bit and see, is it looking like it's starting to look more like our function as we extend n out further around our interval of convergence. Again, paying special attention to our interval of convergence from -1 to 1. Because it's not really true anywhere else, it's only there. Okay, let's take a look at another one. So, find a power series representation of the function, determine the interval of convergence. Again, same directions as before. So the idea here is we want to write this as 1 over 1 minus something. Doesn't really matter what that something is. I'm going to get rid of it, not call it x, because sometimes students have an issue like recognizing that x can be anything. Okay. And that's going to be equal to the sum n equals 0 to infinity of whatever that thing is to the n. And keeping in mind that whatever that thing is, the absolute value of it is less than 1 will be our interval of convergence. Okay, so first of all, how do we make this 2 into a 1? Well, we factor it out. Pull the 2 out. That will leave behind 1. Now on the bottom, how can we make this 3 into a 1? Well, we can factor out a 3. So on the bottom, we're going to factor out a 3. What's left behind is 3 divided by 3 is 1, minus x divided by 3 is x over 3. So this is our ratio, essentially, our r, or in our formula, our x, but whatever. So this means that this is going to be equal to 2/3 times the sum n equals 0 to infinity of our x over 3 to the n. Now, one thing to note is one of the first things that we did when we started talking about our series is reminding you of the rules of our series. So a constant times the series, we can distribute that constant in. In fact, anything that's not based on n can be put in or pulled out of our summation here. Because it's not dependent on n, so it's not varying, it's always the same, so it can be put in or pulled out as needed. And the general rule of thumb is that if I have other 2's in here, or like anything outside, if I have it inside, I'm usually putting it inside. Otherwise, I could just leave it out. So 2, there's no 2's in here, so I'm going to just leave that out as just a constant outside. N equals 0 to infinity. But this 3, I'm going to put it into here. Now, keep in mind, this is 2/3. That was a terrible 3, but whatever. Of x to the n over 3 to the n. That's what this thing is. So when we put this 3 in, because we have a 3 in here, we're going to have 2 times the sum n equals 0 to infinity of x to the n over 3 times 3 to the n. That's going to be 3 to the n plus 1. So this is one of the ways that we can write it. We can also write it just simply n equals 0 to infinity of 2x to the n over 3n plus 1. That's also fine, and I tend to write it like this, but you'll often see it like this, where if there isn't anything inside, we don't bother putting it in. But again, it kind of just depends. They're the same, so who cares? So let's think about what this series looks like real fast. So when n is 0, our first term, 0 plus 1 is 3, 2, and this 3, it just makes 2/3. X to the 0 is just 1, so it's 2/3. Plus, now when n is 1, we still have a 2, and on the bottom we have a 3 to the 1 plus 1, which would be 3 squared. I'm just going to write it as 3 squared, x to the 1, plus the next one, our 2 is still there. It's still just constant throughout. We have 3 to the 2 plus 1 is 3 cubed, x squared, plus 2, 3 to the 4th, x cubed, plus dot, 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 dot. So that's what this looks like. So we're saying that this thing here is a power series representing this function. And again, we need to check that, but first let's find the interval of convergence. So we go back to this thing here, x over 3, that's our ratio essentially in a geometric series. So that is x over 3 absolute value has to be less than 1. So that means that the absolute value of x, because that's the only one that varies, over 3 is less than 1, because 3 is clearly just 3. So that means that if we multiply by 3, we get absolute value of x is less than 3. And so now we can drop this absolute value. X is less than 3 and greater than negative 3. So our interval of convergence is between negative 3 to 3. So this is only true in this interval. Okay, so let's take a look at it again and just see. We have 2 over 3 minus x. Ooh, Control Z. Did not mean to delete that. Okay, so that's what this function is, from negative 3 to 3. That's our interval that we care about here. So here's our function, and now let's take a look at our power series. So we're saying it's 2/3 plus 2 over 3 squared x plus 2 over 3 cubed x squared plus 2 over 3 to the 4th x cubed. And we can see that this is getting better and better, but it's going to take a little bit longer to get there than some of the others because essentially it's being divided by 3, so it needs a little bit more to kind of start to get it there. But we can at least believe, hopefully, that this thing does look like it's starting to approach our function. Okay, let's take a look at another one. All right, so here we have x squared over x to the 4th plus 16 in same directions as before. So again, we're trying to match it to 1 over 1 minus something. I keep going to write x, but I want to make it clear that it can be whatever. All right, and again, this will be the sum n equals 0 to infinity of that thing to the n, and we want to also take the absolute value of that thing and show it's less than 1. Okay, so first of all, how do we make this x squared into a 1? Well, we pull it out, x squared. All right, now, so that's 1. I'm going to reorder this so it's a constant first because we like our constant first, so I'm going to call this 16 plus x to the 4th. Okay. Now, how do we make this 16 into a 1? Well, same thing we did before, factor out that 16. So I'm going to pull out that 16. This will be x squared over 16 times 1 over 16 divided by 16 is 1 plus x to the 4th over 16. All right. Now, this is not quite there because if you notice, we always have had a minus. So I'm going to rewrite this as x squared over 16, 1 over 1 minus a negative x to the 4th over 16. Okay, now, if you think about it, 16, we could also technically write this as the 16. That's like 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's actually a 2 to the 4th as well, if we really wanted it to be. We'll probably rewrite that eventually as that, but at least currently we're okay. It doesn't really matter at this stage. All right, so this now is of the form that we want. So what we're saying is that this function is equal to this thing times this, and this right here can be written as the sum. So basically we have x squared over 16 times the sum, n equals 0 to infinity, of the thing inside our parentheses, negative x to the 4th over 16 to the n. Okay. Now, let's clean this up a little bit. First of all, we notice that this is an alternating series. It's going back and forth between negative and positive because of that negative here. So we can write that in a more normal notation of negative 1 to the n. So basically we're saying that -1 times x to the fourth being raised to the n. So we're taking that n to this -1, and we're taking that n to the x to the fourth as well. There is no distributive property as a reminder of exponents, but when it's a monomial, it looks like it distributes. Okay, so we have a -1 to the n, and then we have x to the 4n, because x to the fourth to the n, that we multiply, so x to the 4n. And this is all over our 16 to the n, which, as you remember, is 2 to the fourth to the n, which is just 2 to the 4n. Okay, so we'll just go ahead and do that as well while we're at it. 2 to the 4n. Okay, so that's what this sum is, and it's still being multiplied by x squared over 16. Now, this x squared and this 16 are not being affected by n, so they can be put into it and pulled out as needed. N equals 0 to infinity. I should have noted that. Okay, so we're going to go ahead and put this x in. We're also going to think about 16. That's like an x squared over 2 to the 4 as well. Okay, so this x squared, I'm just going to put it into our sum. So x to the 4n times x squared is just going to give us the sum n equals 0 to infinity. Our alternating does not change. X to the 4n times x squared is going to give us x to the 4n plus 2 over our 2 to the 4th times 2 to the 4n. Well, we add exponents as well. 2 to the 4n plus 4. So that is our power series describing our function here. And again, we'll take a look at that in a little bit, but let's start with the interval of convergence of this thing. So again, we go back to the thing inside our parentheses. So that is to say this negative x to the fourth over 16th, the absolute value of it needs to be less than 1. So first of all, we're going to use our same logic we did before. Well, a negative of it, that's just going to be the absolute value of x to the fourth over 16 is less than 1. Multiplying both sides by 16, we get the absolute value of x to the fourth is less than 16. We're going to take the fourth root of this thing, and we get the absolute value of x is going to be less than 2. So that means that x is between -2 and 2. So that's our interval of convergence. So we're saying that this is equal to our x, what was it, x squared over 16, x fourth plus 16 on the interval from -2 to 2. So it's equal to this when x is between there. Okay, so let's go ahead and take a look at it. So let's look at our series first of all. When n is 0, this would be a positive, so we know it's a positive. X squared over 2 to the fourth. Okay, minus the next one would be a negative then, it's alternating. So when n is 1, 4 plus 2 is x to the 6th over 2 to the 6th as well, or excuse me, 4 plus 4, that's 8. That's better, Andy. All right, so plus, this would be when n is 2, we would get x to the 8 plus 2, which is 10. So we're going on this by 4 each time, and here by 4 as well. So that would be, again, in 2, 8 plus 4 is 12 here, minus x to the 14th over 2 to the 16th, so on and so forth. So let's take a look at this one. So again, it's between -2 and 2 in this case, because of our interval of convergence. And we're going to say it's x squared over x to the fourth plus 16. Okay, so that's what this function here looks like. And we're going to take a look at our x squared over 2 to the fourth minus x to the 6th over 2 to the 8th. Okay, well, first of all, we're already starting to see that that looks pretty darn good. It's just at those endpoints it starts to struggle a little bit. Plus x to the 10th over 2 to the 12th. And again, we're seeing that that is looking pretty good. All right, so let's take a look at another one. All right, find a power series representation of this function. Okay, so again, we're trying to match it to 1 over 1 plus something. So if we pull out our x, that will leave behind a 1, and we have a 1. So now this plus x, I'm going to write it, I said plus here. It should be a minus, sorry. That's what I get for looking at that thing while I'm writing. Okay, so we're trying to make this plus into a minus. So that's going to be a minus negative x. All right, so that means that this is going to be x times the sum n equals 0 to infinity of negative x to the n. So this is an alternating series. So that is x times the sum negative 1 to the n times x to the n equals 0 to infinity. Okay, now we can put this x into that. That would be the sum n equals 0 to infinity of negative 1 to the n x to the n plus 1, because x times x to the n is x to the n plus 1. So this is our power series. And again, real quick, I'm not going to graph it this time. I think you can trust that they do look good. But let's talk about what this looks like. Basically, we're saying that our function here, x over 1 plus x, is equal to the series here. When n is 0, this is a positive x. Then it's minus x squared plus x cubed minus x to the 4th plus x to the 5th minus x to the 6th, etc. That's what we're saying. Now let's talk about the interval of convergence here. So it is only equal to our function when we're on our interval of convergence. So that is when negative x, the thing inside our parentheses, its absolute value is less than 1. So that is absolute value of x is less than 1. So that is to say x is between negative 1 and 1. So on our interval from negative 1 to 1. This is our interval of convergence. And when we're on this interval, this series is equal to our function. Okay, let's do another one. All right, find a power series again and determine the interval of convergence. So again, we're trying to match this to 1 over 1 minus something. I need to pull that 5 out. 5, that's now 1. Okay, the 1 is good, so we don't really have to deal with it. Minus, the minus is also good. This would be a 4x squared. Okay, so that means that this is going to be equal to 5 times the sum, n equals 0 to infinity, of our 4x squared to the n. All right, so first of all, this 5 here is not being changed to the n, so we don't have to bring it in, but we can if we want. I probably will. We'll see in a little bit whether I do. So we can write this as 4x squared to the n like this, but we can also write this as 4 to the n x to the 2n times 5. We can also then write this as bringing that 5 in and writing 4 as 2 squared, because that's kind of more normal. So 2 squared to the n would be 2 to the 2n, x to the 2n. So this is one of the reasons that we tend to leave that 5 out instead of putting it in, is because it kind of seems to make it a little bit messy. And since it's not really depending on n anyway, we don't have to have it there. So this statement is the same as this one, which is also the same as 5 times the sum n equals 0 to infinity of 2 to the 2n x to the 2n, which technically speaking, if you wanted, you could also write this as 5 sum n equals 0 to infinity of 2x to the 2n if you would prefer. It really doesn't matter. We often kind of split them up, but it's whatever. All of these statements are the same statement. So just something to be aware of. The only thing I would note is that we often don't leave 4. If we can write this number as an exponential as well, or as an exponent, then we might as well do so. Because it's already an exponent. So a value that could be written as an exponent that's being taken to an exponent, just write it as the exponent. It's a little bit more simplified. Okay, now let's talk about the interval of convergence. Again, the parentheses, that is 4x squared absolute value is less than 1. So this 4, that's like saying 4 times the absolute value of x squared is less than 1. So divide everything by 4. We get x squared is less than 1/4. Take the square root of both sides, and we get absolute value of x is less than 1 over the square root of 4. So square root of 1 is 1, square root of 4 is 2. So that means that we are on the interval from -1/2 to 1/2. This is our interval of convergence. So let's take a look at what is this thing, this series then? What does it look like? Okay, when n is 0, this would be 1, and this would be 1, so it would be 5 times 1, okay? Plus, so this is kind of why I also like to have it in this form personally, but anyway. The next one is 1. This would be 5 times 2 squared times x squared, okay, plus 5 times 2, this is now when n is 2, 2 to the 4th, x to the 4th, plus 5 times 2 to the 6th, x to the 6th, and so on and so forth. All right. Let's take a look at another one. Okay, so now we have 2x minus 6 over x squared minus 6x. Okay, now we want to write this thing as 1 over 1 minus something. We have a problem here. Well, the first problem is that this thing here is not something we can do that with in this form. But if you recall, when we were integrating something like this, we use partial fraction expansions or decompositions or whatever we want to call them, okay? But we split this into things that look like a over something plus b over something. That's a binomial. And that's basically what we have here. So we're going to use that to split this up. So let's go ahead and factor this. Also, if something cancels out, then cool, but it doesn't here. So if we take a look at this, we could factor a 2 out of this thing. That would be x minus 3. And on the bottom, this factors as x factors of 5, so minus 5 minus 1. Okay, nothing cancels here. But this is going to be equal to a over x minus 5 plus b over x minus 1. All right, so multiplying everything through by our x minus 5, x minus 1, we're going to see these things cancel. I'm going to distribute this because I'm going to need to anyway. So 2x minus 6 is equal to a times x minus 1 plus b times x minus 5, since these cancel. Okay, so that means that 2x minus 6 is equal to ax minus a plus bx minus 5b. Alrighty, so that means that our x terms here, here, and here, that is 2 must be a plus b. And we also have our constant terms, so negative 6 must be equal to negative a minus 5b. Okay, so we need to solve for these things, but notice these would cancel if we do our elimination. So if we add this row to this one, 2 minus 6 is negative 4 is equal to the a's cancel, and we'd have negative 4b. So that tells us that b is 1. If b is 1, then 2 equals a plus 1, so a is also 1. So we can rewrite this thing, first of all, as 1 over x minus 5 plus 1 over x minus 1. That's what this thing here is. So now that we have these two functions, we're going to rewrite them into a more normal form. Well, they are in normal form, but we want to write them because, again, we're trying to match each of these things to be something of 1, 1 minus something. That's what we're trying to match both of these two. So we're going to treat them each individually, but the first thing I'm going to do is reorder this. So this would be a 1 over negative 5 plus x plus 1 over negative 1 plus x. Next, I need to make this thing here a 1. So that means I'm going to, this one's fine as a 1, I'm going to pull out a negative 5. That would leave behind 1 minus x over 5, which is good because this turns that into a negative, which we like anyway. Plus, over here, the 1's fine. I'm going to pull out a negative 1, and that would leave behind 1 minus x. Okay, so this sum and this sum can both be individually written. This would be negative 1/5, terrible 5, whatever. So that made it even worse. Negative 1/5 times the sum, n equals 0 to infinity, of this thing, x over 5 to the n, plus, over here, this negative 1, so it's really negative, sum, n equals 0 to infinity, of, this is just the normal form, so that would be x to the n. All right, now we have these two sums, but that's a 5. I'm going to put that in there. So this is, again, like x to the n over 5 to the n. N equals 0 to infinity. This is negative 1 over 5. So I could put this 5 in here. I could also put the negative in, but I think it's easier to see it outside, so I'm going to leave it out because it's not alternating. This negative is not alternating. It's not dependent on n. It's just always negative. Okay? And so we're going to put this thing in. This is negative sum n equals 0 to infinity of x to the n over 5 to the n plus 1. Because again, 5 times 5 to the n is 5 to the n plus 1. Oops. Now we're going to deal with this minus here. I'm just going to write minus the sum n equals 0 to infinity of x to the n. Okay, now because these both have the same set point, n equals 0 to infinity, I mean, we can really combine them. So that is to say, negative sum infinity n minus equals 0. If we factor out, let's start by factoring out negative out of both. If we factor out negative out of both, okay, that would be x to the n over 5n plus 1 plus the sum n equals 0 to infinity of x to the n. So pulling that negative out, since they're both negative. Now we can apply our rules of summations where the sum of two summations, we can just add them together. So that would be negative sum n equals 0 to infinity of x to the n over 5n plus 1 plus x to the n. Okay, so that's what our sum looks like. And we can certainly simplify this. They both have an x to the n, so I'm going to factor it out. Not out of the sum, but just out of this binomial here. Sum n equals 0 to infinity of x to the n. That leaves behind 1 over 5n plus 1 plus 1. Now, we could also combine these if we wanted. In this form, this is fine, but you can also combine them. It'd be easier if they're combined when actually trying to figure out what this series looks like. So I'm going to go ahead and do that. This needs a 5 to the n plus 1 top and bottom, in which case we would have negative sum n equals 0 to infinity of x to the n times 1 plus 5 to the n plus 1 over 5 to the n plus 1. So these are both equivalent. This is equivalent. These are all equivalent. This one is sometimes left as is here. The benefit of this one is that it's going to make our series really easy to find. So that is to say, well, what's our first term? When n is 0, this would be a 1. That'd be a 5 and a 1, so it'd be like 1 plus 5 over 5. I know it's 6 over 5, and then it's a negative of it. So then we have minus, but I'm going to leave it like here because you'll see it's just going to be easier form. When n is 1, we'd have x times 1 plus 5 to the second power over 5 to the second minus x squared, 1 plus 5 cubed over 5 cubed minus x cubed to the fourth, so on and so forth, okay? So this is what we're saying this function is equal to, and we'll see that. But let's now take a look at our intervals of convergence. Well, essentially we have two intervals of convergence. We have this one and that one. So we have to consider both of them. So I'm going to go back to this sum here, bring them down. Okay, so essentially x over 5 to the n, that would be the absolute value of x over 5 is less than 1. So multiplying by 5, absolute value of x is less than 1, less than 5. That means that x is between negative 5 and 5. Now over here, this would just be x is less than 1. So that means that x is between negative 1 and 1. Now, which one is this? Well, it's got to be true for both of them. And while negative 4 would work in this one, it wouldn't work in this one. So our interval of convergence would just be on negative 1 to 1. That's our interval of convergence, the most restrictive of the two. So the overlap, essentially, of the two. So let's take a look at this really quick and see if we are getting there. Because again, this one might be a little like, are we sure about that? So first of all, our interval is from negative 1 to 1. We would have 2x minus 6 over x squared minus 6x plus 5. All right, so we are now saying we are trying to match this thing with our power series that we just wrote. So let's take a look at it. Again, this is negative 1 plus 5, which I know is 6, but I just have it in that form because it's easier. Minus x, 1 plus 5 squared over 5 squared. That's looking decent. I mean, it's a straight line right now, but we'll deal with it. X squared, that will put a curve into it, times 1 plus 5 cubed over 5 cubed. All right, so as you see, that's looking pretty good. It's definitely starting to appear to match it. So that will be sufficient after this one. 5 to the 4th. Yeah, I would agree that that looks pretty good. Okay. Okay, so now let's take a look at this one here. We have f of x is equal to x minus 1 over x plus 4. So in this one here, we can't use partial fraction decomposition because this thing here is the same power as this one, or greater than. So we have to start with some division. So that means that x plus 4 is divided into x minus 1. Okay, so x times 1 would make it x. So 1 times x is x. 1 times 4 is plus 4. And then we are going to flip the signs, draw our line here. This cancels. Negative 1 minus 4 is negative 5. So that's our remainder. So we'd say plus negative 5 over x plus 4. Okay, so what we have here then is 1 plus negative 5 over x plus 4. This is what this function is. So again, we want to match it to 1 over 1 minus some quantity. Okay. Okay, now this 1 is just 1. It's a constant, it's 1. It's not varying with respect to anything. It is a constant. And because it's a constant, it's just going to be 1 plus our sum, which just kind of adds the 1 to it. So we'll deal with that in a bit, but let's first write this sum here. So this thing is a sum. I need to pull out a negative 5. That leaves behind 1. I'm going to reorder this. This would be a 4 plus x. Okay, now I'm going to pull out a 4, so that's a negative 5 over 4, 1 over 1 plus x over 4. All right, but we need to write this as a minus, so this would be negative 5/4. Again, this is 1 plus all of this. 1 over 1 minus negative x over 4. Which, if you remember, 4 is going to be like 2 squared if we need to write it later, but anyway. So that means this is 1 plus the sum, n equals 0 to infinity. We have a negative 5/4 outside our sum, so I'm going to keep it there. This is our sum. That's negative x over 4 to the n. Okay, so that means that this is 1 minus 5/4 sum n equals 0 to infinity. This is an alternating series. That would be a negative 1 to the n, x to the n over 4 to the n. Okay. Now sometimes if it's alternating and we have a constant, we just throw that negative into that constant as well, but it's whatever. We'll deal with that. Okay, so Now what we want to do is we want to put this 4 into this 4 to the n. So that means that we have 1, and we'll do the minus as well. So this minus, if we put that in, that's like saying a -1 is being multiplied by this. So -1 and -1, that's going to be the sum. That was a terrible sum. Let me try that again. Sum n equals 0 to infinity. The -1 into this gives us a -1 to the n plus 1. All right. The 5 is okay. I'm going to leave it as 5. There's no 5's inside. X to the n. But this 4, that would be a 4 to the n plus 1. So we have our sum here. This is our sum. And you might go, okay, well, what does that mean we have? Well, this is 1 plus it. So it's 1 plus, and then we take a look at this sum. When n is 0, 1, it's a -5 over 4 to the 1, so 4. Then it alternates, plus. Okay, so it's a minus here, plus. All right, so now when n is 1, we are going to go with, this would be a positive. That's why we have a plus. X, all right at the end. 5 is always being multiplied by it, and then 4 squared. Minus 5x squared over 4 cubed plus 5x cubed over 4 to the 4th minus ... That's what this looks like. So that 1 is just in front of it. It's just 1 plus. Okay. And so, again, it's a sum, and, you know, if it converges absolutely, the order doesn't matter, but whether it converges absolutely or not, you know, we have that 1 in front. So yeah, and it does converge absolutely because it's a geometric series that we're creating on this interval of convergence, so it would be an absolute convergence. So we could put this 1 at the end if we wanted, or anywhere else if we wanted, but in the front it's fine, where it belonged. All right. So let's talk about the interval of convergence now. So we need to go back to this parentheses here. So that is this thing, -x over 4. The absolute value of -x over 4 has to be less than 1. So that means x absolute value has to be less than 4. So that means that we're from -4 to 4 is our interval of convergence of when this would be true. All right. So let's now talk about differentiation and integration. So the sum of a power series is a function whose domain is the interval of convergence of the series. Okay. So again, it's just this function, some constant times x minus a to the n, where a is our kind of center. As a reminder, c sub n is just some constant, and it can be dependent on n. So it might be varying with n, so it might be like 4 to the n or whatever, like in this previous one here. Okay, and notice I did write it as 4 to the n plus 1 here. I could have also written this as 2 to the 2n plus 2 if I had wanted to. I don't know why I didn't on this one when I did on previous ones. Probably because I just forgot. Doesn't matter. Okay, so that's what this c sub n is just like some constant, potentially dependent on n, most likely dependent on n, but it doesn't have to be. It's just constant. Okay, if we want to differentiate or integrate these functions, we can do so by integrating each individual term in the series just as we would with a polynomial. This is called term-by-term differentiation and integration. So let's go to our most basic one, x to the n. Okay? If we think about this, this is like the first term would be 1 plus x squared plus x cubed plus x to the 4th plus ... Okay, and so the derivative of this thing, if we were to derive it, so that is f prime of x then, would be the derivative of 1 is 0, plus the derivative of x is 1, plus the derivative of x squared is going to be 2x plus 3x squared plus 4x to the 3rd plus ... Okay, so let's think about what this thing would be. First of all, notice we shifted. So starting at 0, we actually start at 1. And so this sum actually starts at 1 when we differentiate it. And so then we'd have something like x to the n minus 1 here. Okay, so if if this is 1, that would at least force this to be a 1. So 1 minus 1 is 0, that x to that 1. But notice that the next one is a 2 to the x. So when n is 2, we would get x, which would work, but we still need a 2. So it was 1 before, now it's 2. So our first term was 1, so if we call that n, then we'll then get this to work out, because n is 1. This would be a 1 here. X to the 0, so it's just 1. When n is 2, we'd have 2x to the 1. 3, 3x squared, 4, 4x to the third, and so on and so forth. Now notice, think about this. This was the sum of x to the n. If we were to derive x to the n, we would get n x to the n minus 1. That's what this is right here. But we again are shrunk on here. We can also shift this over if we want. So if we want to start at 0, okay, think about it. We're subtracting 1 here, so each one of these needs to go up by 1 to balance it out. So minus 1 plus 1 to each. So that would be n plus 1 to the n. N plus 1 times x to the n, like this. Okay, and we can double check that this works out still. 0 plus 1 is 1, x to the 0, 1. So even though it starts at 1, this is what we usually write it as, but it starts at 1, fair enough. We can always shift them to start at 0 or start at 1 as needed. Okay, now let's think about the integral now. So capital F of x. Okay, well, if we integrate this thing, first of all, if you remember, when we integrate a polynomial, or really anything for that matter, we need a plus c. So it's actually, and I'm going to put it in front, plus c here. Okay, integral of 1 x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. So this lines up here, this one here. Integral of x squared is x cubed over 3, x to the 4th over 4, and x to the 5th over 5. So this constant was not from here, it's just there was some constant that we might have gotten that would have dropped off and not be visible in our function here. So we need that constant of integration. So that means that this is constant plus the integral n equals 1. We're still starting at 1. This is our first term, or excuse me, 1. At our first term, which was n equals 0, I'm sorry. N equals 0, so this was n equals 0 here, so they are still starting at n equals 0. Okay, to infinity. These are all infinity, I didn't write them. Okay. Now, let's think about this one here. I want my first term to be an x, so I need an x to the n plus 1. That would ensure that this 0 gives me an x. Okay, now the next thing I need to do is make sure that you know, the first one is just over 1, but the next one is 2 and 3 and so on. So it's over n plus 1. Because again, 0 plus 1 is 1. That's good. 1 plus 1 is 2. 2 plus 1 is 3, and so on and so forth. Which, if you recall, I mean, if you were to integrate x to the n, okay, this would be x to the n plus 1 over n plus 1. That's how you integrate x cubed or something like that. So that checks out. This is literally our integral. It's c, our constant of integration, plus the summation of this thing. Okay, so let's take a look at that's officially going to be defined here. So if the power series, c sub n, x minus a to the n has a radius of convergence r greater than 0, then the function f is defined by this statement, c sub naught plus c sub 1 times x minus a plus c sub 2 times x minus a squared, so on and so forth, which can be written by this series. So this is differentiable and therefore continuous on the interval a minus r to a plus r, our interval of convergence of our original function. So it is differentiable and continuous on that. And f prime of x is equal to c sub 1. So that is shifting over because that constant drops off, c sub 1 to c sub 2, so on and so forth, which would just be n, c sub n, x minus a to the n minus 1. Again, exactly what I had, only now we're allowing for our center to not be at 0. And our integral is some constant plus the summation n equals 0 to infinity of c sub n of x minus a to the n plus 1 over n plus 1. And again, the radius of convergence of both of these power series is also r, so they have the same radius of convergence. Okay, so again, this is just the official definition of it, and this allows for us to deal with really anything here. A few things to note, though. First of all, although the radius of convergence remains the same when a power series is differentiated or integrated, this doesn't mean that the interval of convergence remains the same. So it may be that the original series converges at some endpoint where the differentiated series diverges there. So like if we had some function that converges at the endpoints, -1 and 1, if you were to find the derivative, it's very likely it would not converge at -1 to 1 because we're dealing with open intervals on derivatives and stuff like that. But something to be aware of. But it still has the same radius. It is still from -1 to 1. It's just that now we can't do the endpoints. That's all we need to know here. Okay, so find a power series representation for this function and determine the interval of convergence. All right, so basically, in something like this, the idea is that we are going to use our basic power series, 1 minus some quantity, this thing, 1 over 1 minus some quantity, to write our sum, n equals 0 to infinity of that thing to the n. That's what we want to do. And then we want to find something that will enable us to then take the derivative of this or the integral of this to get to here. And we might have to do some adjustments and stuff to the number, like, you know, multiplying a constant or whatever. But in general, the idea is we want it to be something close to it at least that we can then manipulate to force it into this form. So what we're going to do is we're going to look at this and go, all right, well, if I had a power series, and in general what I do is I kind of just start at ignoring the powers. What if I had 1 over 1 minus x? What if I did this thing? Well, clearly I could write this as the sum, because it's in the perfect form, x to the n equals 0 to infinity. All right, these two things are the same. So what if I take the derivative of these things? So d dx of 1 over 1 minus x. Then I derive this one as well. So let's take the derivative of this. That would be 1 minus x to the -1 that we're taking the derivative of. So that would be -1 times 1 minus x to the -2 times the derivative of the inside, -1. So negative and a negative makes a positive, and we get this 1 over 1 minus x squared, which is exactly what we wanted. So this thing comes from the derivative of 1 over 1 minus x. And we can write 1 over 1 minus x as this. So that means that this thing is equal to the derivative of our sum, n equals 0 to infinity x to the n, technically our series since it's an infinite sum, but I say sum a lot in that case. All right, so we're taking the derivative of this thing. That's what would get us this thing. So when we're taking the derivative, as a reminder, first of all, our series starts at 1 because basically what's happening here is that here's our original series, x to the n, and when we take the derivative of it, we lose the first term. So we're essentially shifting our series to start at n equals 1 instead of 0. When we integrate that, it's actually the opposite. This is where our n equals 0 is. This would be n is -1, sort of, but we don't do that. And so instead of shifting to the left to n equals -1, what we do is we keep it at n equals 0 and then just add our constant to the left of it, which basically shifts our whole series over. All right. So that's what we're doing here. When we derive this, we lose the constant term, so we don't need to start at n equals 0. We start at n equals 1 to infinity, and the derivative of x to the n is the power rule, n x to the n minus 1. This is 1 over 1 minus x squared, and these are both functions of x's on our interval of convergence. So let's think about this thing. What is our interval of convergence now? So our interval of convergence is just going to be the interval of convergence of our original power series here that we wrote. So that is to say, we're looking at this thing, and we're saying, well, x absolute value has to be less than 1. So that means that x is between -1 and 1. So our function, 1 over 1 minus x squared, is equal to our power series nx to the n minus 1 from n equals 1 to infinity. But we could actually clean this up a little bit better because n equals 1, while that's true, we often like to start at n equals 0. So if we write this as n equals 0, essentially we're subtracting this by 1 so to make up for the minus 1 here, we're adding 1 to each of these n's, so n plus 1, and x to the n minus 1 plus 1 is just n. So this is what our function 1 over 1 minus x squared is on this interval. So we can double check this. It's easiest to graph it. I find that's kind of the easiest way to make sure that what I have is true. So first of all, let's think about this in terms of our series. So if we're writing this series, when n is 0, 0 plus 1 is 1, x to the 0 is 1, so it's 1. Plus, it's not alternating, n is 1, 1 plus 1 is 2, x to the 1. Plus, when n is 2, 2 plus 1 is 3, x squared, plus 4x cubed, plus 5x fourth, plus 6x fifth, plus dot, 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 dot. That's what this thing is. And let's see if it's a good approximator for our function here. So f of x is equal to squiggly brackets from -1, x1. So that's setting my boundaries. There we go, that's better. And this is 1 over 1 minus x squared. Okay, so this is the function that we're trying to write as a power series. So this is 1 plus 2x, okay, plus 3x squared plus 4x cubed. And if you look, I mean, this is definitely looking pretty good already. Like it's definitely following that general curve. Plus 5x to the fourth, plus 6x to the fifth, and so on and so forth. And we can continue this as many times as we need to get it as accurate as we want it to be. So, but again, I'm just checking this to make sure that what I have checks out. Like this is an approximator to this, because this thing is equal to it, and this partial sum would be an approximation to it. So I just want to make sure that I'm ballparking it. Okay, let's take a look at another one. So find a power series representation for this function and determine the interval of convergence. Okay, so same idea. Again, I'm ignoring the powers. And I'm trying to write this as like 1 over 1 minus something. Okay, so ignoring the powers, I'm going to start here and work from there. So I have something like this. If I was trying to write this into this form, well, I would factor out the 3 on the bottom. So pulling out that 3, we get 1 plus x over 3. And I also want this as a minus, so I'm going to rewrite this as well as 1/3 times 1 over 1 minus negative x over 3. That's where I'm going to start. Okay. So essentially, this is our is kind of a starting point. And we can write this thing as a series. So if we think about this thing as a series, that's 1/3 times sum n equals 0 to infinity of negative x over 3 to the n. Okay. Now, I might be getting ahead of myself because I should really double check that this is the same thing as this. Okay, so let's give it a shot and see, or at least something close to it. So in order to go from here to here, probably a derivative. So 3 plus x to the -1, that's what we have. If we take the derivative, it would be negative 3 plus x to the -2 times 1. So not really worth mentioning. That is to say it's negative 1 over 3 plus x squared, something like that. Now, that's pretty close to this, but not quite right. So if we think about it, again, d dx, where we got this was the derivative of 1 over 3 plus x. This is equal to negative 1 over 3 plus x squared. That's what this thing is equal to. And so, essentially, if I want to make this quantity, because this is really what I'm trying to write my power series for, is 1 over 3 plus x squared, not negative 1 over 3x plus squared. What I need to do is, well, f of x then, which is equal to 1 over 3 plus x squared, this thing is equal to negative negative 1 over 3 plus x squared, right? Like this thing, it's the opposite sign to this quantity. That is to say, it is negative derivative of our 1 over 3 plus x. It's the opposite sign to whatever the derivative of this thing is. So that's how we can force our derivative into the form that we actually need it to be, is just switch the sign. Okay, so we wrote this 1 over 3 plus x as a power series, but let's clean it up a little bit. That would be 1 over 3 integral n equals 0 to infinity of, this is alternating series, so negative 1 to the n, x to the n, all over 3 to the n. Now, this 3 can be put into here, so we can actually write this, and I'm just going to make a bit of room for it. Okay, we can write this 3 times 3 to the n is just going to be sum n equals 0 to infinity of negative 1 to the n, x to the n, over 3 to the n plus 1. Okay, so this is our 1 over 3 plus x. That's what this power series is. And again, our power series that we're looking for should be the negative of the derivative of this thing. Okay, so that is to say, f of x, which is equal to 1 over 3 plus x squared, the thing that we're trying to solve for, is going to be equal to negative derivative of our sum, n equals 0 to infinity of negative 1 n x to the n over 3 to the n plus 1. All right, so when we're deriving something, as a reminder, constants are not changed. There's constant multiples just stay the same. So this and this do not change. It's going to be negative sum n equals 1. We shift it to the right because we're deriving it. Integral. Now, this stays the same, negative 1 to the n. This thing stays the same, 3 to the n plus 1, because they're both constants. Our x to the n is the only thing that we're deriving, basically. We're doing the power rule. N comes down in front, n, x, n minus 1. So n comes down in front, x to the n minus 1. This is our 1 over 3 plus x squared. Now, we can do a bit of cleanup work, but that is it. So first of all, I'm going to put this negative into this thing, because this is like a negative 1 times here. So same base, all right, add their exponents. So n equals 1 to infinity. That would be negative 1 to the n plus 1 over 3 to the n plus 1. Now, because our constants are both to the same power, I'm going to probably write those together just to make it a little bit nicer. So that is to say, we'll take sum n equals 1 to infinity of negative 1 over 3 to the n plus 1. So that's one way we could write this, n x to the n minus 1. All right. The other option is to keep them separate, because we are going to switch this out here, and I don't like starting at n equals 1. I'm going to start at n equals 0. So n equals 0 to infinity. I'm going to so I subtracted this by 1, so to balance that out, I need to add 1 to each of the n's. So that would be negative 1 over 3 to the n, so we're adding 1 plus 2 times n plus 1. We added 1 to n, and we get x to the n. n minus 1 plus 1 is just n. All right, so this is our sum. This is our 1 over, or our power series for 1 over 3 plus x squared, right here. Now, we can double check that this is going to work out, but before that we do that, let's first find our interval of convergence. So again, basically what I'm doing is I'm going back to my basic power series, my ratio here, this negative x over 3, and I'm going, okay, the absolute value of negative x over 3 is going to be less than 1. So this means that this is equal to absolute value of x over 3 is less than 1. Multiplying both sides by 3, we get absolute value of x is less than 3. So x is between negative 3 and 3. This is our interval of convergence, and it is this. All right, I'm going to copy it and paste it down below so that we can take a look at it a little bit more. So let's talk about what this series actually is. So the first term, n equals 0. 0 plus 2 is going to be a positive 1 over 3 squared times n plus 1, which is just 1, times x to the 0, which is just 1. So I don't really need it. So really, this is just going to be that thing, positive. It's an alternating series. The next one should be a minus. We'll double check though. 1 plus 2, that would be a negative. So it's 3, so it's 3 to the third. So it's negative 1 over 3 to the third times 1 plus 1 is 2 times x to the 1. Okay. Plus 1 over 3 to the fourth times 3 x squared minus 1 over 3 to the fifth times 4 x to the third plus dot dot dot. All right, so let's go ahead and take a look and see if this is true. So first of all, our interval of convergence is from negative 3 to 3. Our function is 3 plus x squared. So this is what we're trying to approximate with our partial sum here. I mean, again, we are saying that these are equal because they are equal, but I don't want to type out infinite values, so I'm just going to do a partial sum and just see if it's looking correct. So 1 over 3 squared minus 1 over 3 cubed, well, times 2, so 2 over 3 cubed x, okay, plus, let's go ahead and bring this so I can actually see it. All right, 3 over 3 to the fourth x cubed. Oh, I think I'm x squared. There we go. Okay. Minus 4 over 3 to the fifth x to the third. Okay. And I think we can see that this is starting to definitely take this shape. I mean, it's definitely following this curve here. It goes a little bit off here. But basically what's causing this is just because this bottom here is kind of, it's just taking a little bit longer for us to get to where it's definitely like really close. But again, that just means we have to take that partial sum out further. So 5 over 3 to the sixth x to the fourth, and so on and so forth. But we can definitely see that it's definitely looking like it. All right, so that checks out. Okay, let's take a look at another one. Find the interval of convergence and power series representation for this function. Okay, so we have ln. All right, now how can I get like an ln from 1 over 1 minus something? Well, if I integrate something that's in this form, then it should be an ln. Essentially, the derivative of ln, 5 minus x, will give us like a 1. So if you think about this, d dx of this quantity here would be 1 over 5 minus x times negative 1. Okay, so that is to say negative 1 over 5 minus x. That's what this thing would be. So this is our f of x, but our f prime of x, excuse me, if we call this f of x. Okay, so if this is f of x, this is f prime of x. Now this is basically in the form that we want it to be in. So what we can do then is we can keep in mind that if we rewrite this into this form and write it as a power series, then we just integrate that thing to get back to here, because the integral of f prime will just go back to f. Okay, so let's go ahead and do that. So let's get this into the form that we want it. First of all, this negative whatever, I'll pull that negative out. Okay, and on the bottom, I'm going to pull out a 5. That leaves behind 1 over 1 minus x over 5. So this is what our f prime of x is equal to. Okay, so that then tells us that we are in the right form we need. It's negative 1/5 times the sum n equals 0 to infinity of our x over 5 to the n. Okay, so this is what our f prime of x is equal to. Okay, so we can clean this up a little bit. That would mean that this is negative sum n equals 0 to infinity. So x over 5 to the n is x to the n over 5 to the n. And this 5 here, I'm going to put into it. So we have x to the n over 5 to the n plus 1. And we have this negative. We could put the negative in as well, but if it's just here, I'm going to leave it out. If there's no alternating series in here, then this negative doesn't really have anything to go with, so I'm just going to leave it outside. So this is our f prime of x. So if we want to find f of x, we just have to integrate f prime of x. So we're going to integrate this thing. So the integral of negative sum n equals 0 to infinity of x to the n over 5n plus 1. Keeping in mind that 5n plus 1 is a constant, so it really doesn't do anything. All right, so when we take the integral of this, as a reminder, it technically shifts it to where n would then be negative 1. So it shifts it to the left, but to account for that, we just do c. So f of x is equal to c, constant of integration, plus negative integral of our sum n equals 0 to infinity of x to the n over 5n plus 1. So again, that negative just pulled out. So again, this constant we ignore. I mean, it's going to still be there. So that is f of x is equal to constant of integration minus the sum n equals 0 to infinity. The 5 to the n plus 1 stays the same. X to the n, when we're integrating this, we raise the power by 1, so it'd be x to the n plus 1, and then we divide everything by n plus 1, the new power here. Again, keeping in mind that if we had the integral of like 3x squared, let's say 3x fourth, that way the numbers aren't the same, dang it. All right, so what we get would be the constant stays the same, and it would be 3x to the fifth. We raise the power by 1 and divide by that new power 5, right? So that's what we're doing here. Nothing different. Okay. So we are here. Okay. So if we want, we can find what c is. Well, what is c? Well, the way you find c is f of 0, basically. So that is, we're going to find c when x is 0 in our function, ln of 5 minus x. So basically, it's when x is 0. So instead of x, we're going to put 0 minus 0. So that is to say our c is natural log of 5. So we're saying that our function, which was natural log of 5 minus x, can be written as the power series ln of 5 minus the sum n equals 0 to infinity of x to the n plus 1 over 5 to the n plus 1 times n plus 1. So let's take a look and see whether this is a good approximation or not. Or a partial sum would be a good approximation, whether this is true or not. So let's think about our first thing. So first of all, ln 5 would be our first one. Then we'd have minus, when n is 0, 0 plus 1 is 1, so that's going to be x over 5 times 1 minus x squared over 5 squared times 2 minus x cubed over 5 cubed times 3 minus x to the 4th over 5 to the 4th times 4 minus dot dot dot. So let's go ahead and take a look at it and see. Oh, we should note, what about our interval of convergence? So before we really go looking at that, let's take a look at the interval of convergence. Well, we go back to our basic power series here. X over 5 is n to the n. So we know that our ratio here, so if we have x over 5 is less than 1, then that tells us that x is between -5 and 5 at least. So what we'd say is the radius is 5. It could be that it's between 5 and 5, it could have endpoints because we're integrating this thing, basically. It could actually include the endpoints, but let's just say for now it's just negative 5 to 5. In order to check it, what we do is we just plug in negative 5 and 5 and see if it converges or not. So when x is negative 5, does this converge? When x is 5, does it converge? Does the series converge? That's all we have to do is just plug it into our power series and see if it converges. But for us, let's just worry about checking this thing. Okay, so it's from negative 5 to 5, and we're talking about ln of 5 minus x. Okay, so, I mean, first of all, in our function in general, negative 5 is undefined. So I would say that it's probably not going to include negative 5 because that would cause an undefined moment anyway. And at 5, it could potentially be it, but if we look here, I mean, it seems like it's having issues at this 5. So let's take a look at it. Ln of 5 minus x. I mean, that's a vertical asymptote right there. Okay, but so I guess that's really what I should have had. At 5, this is our issue because it's a 5 minus x. I was thinking x minus 5. So we have an issue at 5. So 5 definitely isn't included, but negative 5, it might be. Anyway, so let's take a look. Ln of 5 minus x over 5 minus x squared over 5 squared times 2. All right, so we can see that that's starting to look pretty good. Now this is a log, so I imagine it might take a little bit more to get it like really, really good, just because of what logs do. But we can at least see that it is definitely following this general curve. So that checks out. 5 to the 4th, I'm just doing one more. Okay, so again, yeah, I could believe that that is true. All right, so that is our, again, our power series for ln of 5 minus x. Okay, so now that we know the radius of convergence here is 5, we know that it's at least negative 5 to 5. Now, realistically speaking, it's probably not 5 because if we think about it, looking back here, 5 minus 5 is 0, natural log of 0, undefined. So you can't really even include that anyway. But negative 5, it definitely could, potentially. It does exist there. So we'll go ahead and check to see because we integrated this. So we have the potential, since we got from our other one, we integrated our other one, we have the potential to increase our interval to the endpoints. Again, thinking back to kind of some basic integration rules is when we derive things, they're on open intervals, but when we integrate, we can integrate on closed intervals. So just something to keep in mind here. So we can check these intervals of convergence. Basically, we have to check the endpoints because our ratio test wouldn't tell us anything about this, and our geometric series won't really tell us anything about it, basically because it's going to equal 1 at those points. So we're going to have to do some other tests. So basically what we're going to do is we're going to look at our sum, and specifically we only really need the series portion of it. We don't need this portion. We're really just interested here. So we're going to try negative 5. We'll also try 5, but it's not going to work most likely, but it's worth noting it anyway if we're not sure. So if we plug in negative 5, we would have the sum, n equals 0 to infinity, of negative 5 to the n plus 1 over 5 to the n plus 1, n plus 1. Okay, now that's going to be negative 1 to the n plus 1 times 5 to the n plus 1 over 5 to the n plus 1, n plus 1. So essentially, these cancel, and the reason why I pulled that negative out, because it's like saying negative 1 times 5, so we can do that. These two cancel, and we're left with an alternating series, negative 1 to the n plus 1 over n plus 1, sum n equals 0 to infinity. So this is an alternating series, and we can use the alternating series test to test for convergence. So all we have to show is that 1 over n plus 1, that is the b sub n portion of it, the non-alternating part, goes to 0 as the limit as n approaches infinity. So first of all, does this go to 0? Yes, it does. 1 over infinity would be 0. So that's check 1. The next thing we have to check is that basically our b sub n plus 1 is less than b sub n for all n. So that is 1 over n plus 1 plus 1, which would be n plus 2, is less than 1 over b sub n, n plus 1 here. And that's true because the power, this is a larger number on the denominator, so it's definitely going to be less than. So that checks as well. So it converges at -5. So we are not just in from -5 to 5 like that, we're actually including -5. Okay, now we can check 5 with the same logic. The only difference between 5 and -5 is we won't have this alternating series portion of it. So we'll just end up with a 5 to the n plus 1 over 5 to the n plus 1 times n plus 1, like that. That was a terrible infinity. Try that again. So anyway, these cancel, and we get 1 over n plus 1. Now, this is essentially a p-series. I mean, if we think about this, 1 over n plus 1 is less than 1 over n. Now, this is a p-series, and it diverges because the power here is 1, so it's a divergent p-series. And this is less than it, so that direct comparison doesn't tell us anything about this converging or diverging. Since this diverges and this is less than, we don't really know if it diverges. But we can make the assumption, I mean, realistically speaking, I think we can see that the difference between these two is minimal, so there's really no way that this would converge, very likely. So, but that's not very mathematically rigorous. So instead, what we're going to do is we're going to take the limit as n approaches infinity of the ratio of these two things. So essentially like 1 over n plus 1 and 1 over n. And what we want to see is, I was doing the ratio test there. What we want to see is that if we take these two things as this goes to infinity, if it goes to a constant, some constant that's not infinity, then they're going to both converge or both diverge. So if we take this to infinity, we get 1 over n plus 1 times n over 1, which is going to be n over n plus 1, which at infinity is just going to be 1. And so then if this is 1, this diverges, so this also diverges. Okay, so again, it was what we expected because it doesn't even exist at 5, but it's worth noting that we can also show that. So this is our interval of convergence. This is our radius. It's still 5 like normal, but our interval here, because we integrated it, has a potential to include the endpoints. All right, let's take a look at another one. Find a power series representation of this function and determine the interval of convergence. Okay, so we have 1 over 1 plus x squared. Okay, now this is kind of similar to one of the other ones we've done, but it's not quite the same. So again, we want to write this as 1 over 1 minus negative x, something like that. That's what this 1 over 1 plus x would be. Again, I'm ignoring this power, just as a starter position to get a power series written down. So that's going to be the sum, n equals 0 to infinity, of negative x to the n, which would be the sum as n equals 0 to infinity of negative 1 to the n, x to the n. Okay, so this is a sum describing this thing, which is really similar to this, but not quite the same. So now we need to check, like, how can we make this using these things? All right, so probably the derivative. So if we dx are 1 plus x to the negative 1, we're going to get negative 1 plus x to the negative 2 times 1. So it's going to be negative 1 over 1 plus x squared. And so this is going to be equal to the derivative, ddx, of our sum, n equals 0 to infinity of negative 1 n x to the n. That's what this negative 1 over 1 plus x squared is. It's the derivative of our power series, the derivative of our function here, 1 over 1 plus x. Now, this is not quite this, but we can see that in order to get from here to here, 1 over 1 plus x squared is just going to be a negative 1 times negative 1 over 1 plus x squared. That's all it is. It's just the opposite sign to it. So all we have to do is take negative 1 and multiply it by the derivative of this thing. That is to say, we're just taking negative 1 and multiplying by the derivative of our power series, n equals 0 to infinity of negative 1 to the n, x to the n. That's all we need to do to get this one, is multiply this by negative 1, the derivative of negative 1. So if we derive this thing, so 1 over 1 plus x squared is going to be equal to negative 1 times the sum, n equals 1 now because it's derivative. We're shifting it to the right, to infinity. Constant stays the same, negative 1 to the n. This would be n x to the n minus 1. So again, power rule, bring that power down. Okay, so now we're just going to do a bit of cleanup work. I'm going to put this negative 1 in. So we get the sum n equals 1 to infinity of negative 1 to the n plus 1, n x to the n minus 1. And we might as well, while we're at this, write this as a 0 here. So we're going to start at 0. Whoa, terrible sum. All right, n equals 0 to infinity. We're subtracting this by 1, so all the n's need to add by 1. So this would be negative 1 to the n plus 2, n plus 1, x to the n. Okay, now the only thing I would mention too here is that this n plus 2 is pretty meaningless, because if you have a negative number, negative 1 here, if it's to an even, it's going to be positive. If it's to an odd, it's going to be negative. So this plus 2 adds nothing to that even or odd concept. So if n is even, it's going to be even. If n is odd, it's going to be odd. So this plus 2 is pretty meaningless. So really, we shouldn't write it there. We should write this as negative 1 to the n, n plus 1, x to the n. So basically, with your alternating portion, you really only write it as n, n plus 1, or maybe n minus 1. N plus 1 and n minus 1 are equivalent, but it's kind of just a preference thing. But the n is what we want to write when we just want to keep the sign to whatever, like even or odd, that we're dealing with. It goes to, again, we can write it infinitely many ways. N plus 2, n plus 4, n plus 6, those are all the same as n. Just like n plus 1, n plus 3, n plus 5 is all the same. So we really want to just keep it as simplified as possible. All right, so that is our power series describing our function 1 over 1 plus x squared. So as a quick reminder, this thing as a, if we write this thing out as a partial sum, this would be, our first term would be 0 here. So negative 1 to the 0 is 1. 0 plus 1 is 1. X to the 0 is 1. So that's a 1. Minus 2x plus 3x squared minus 4x cubed plus 5x fourth minus dot 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 dot. That's what this thing is equal to. So we're going to go ahead and compare it to the graph in just a sec, but let's first think about our radius of convergence. If we go back here, our negative x to the n, or this this portion here, really, this negative x to the n, this is our ratio, as a reminder. So negative x is less than 1, so that means our interval is from negative 1 to 1. And again, since we're deriving it, it's not going to get any bigger. It would just stay the same. So, or get smaller. So this is our radius of convergence, and we're going to go ahead and take a look at whether or not these two things look similar. 1 over 1 plus x squared. Okay. And we have 1 minus 2x plus 3x squared. 1 1 over 1. Okay. I should shrink this down a bit. So I'm just looking at the part that I care about. F of x is equal to squiggly bracket -1 less than x less than 1. Okay, so we're just looking at this portion here. So this is minus 4x cubed plus 5x to the fourth. I think we can agree that this looks pretty similar. All right, cool. So let's take a look at another one. All right, find a power series representation for the function and determine the interval of convergence. Okay, so in this one here, okay, f of x is equal to tangent -1, tangent inverse x, or arctangent x, whatever we want to call this. You might go, ooh, okay, well, shoot, I don't know how to write tangent as like a 1 over 1 minus something. But if we remember the derivative of tangent inverse x, okay? So if we remember, f prime of x would be 1 over 1 plus x squared, okay? Which is kind of similar to our previous one, but definitely not the same because it's not including this whole thing squared. It's just that. So basically the idea here is, well, this derivative is pretty close to the format we need. In fact, if we rewrite this 1 over 1 minus -x squared, it's now in the format we need. So we can write that as a sum. This is a sum n equals 0 to infinity of -x. I should make this a little bit clearer. It's not -x squared like that, because then that would have canceled the negative. It's like that. So let me fix that. -x squared, like that, to the n. Okay, so that is to say this is equal to, the sum n equals 0 to infinity of -1 to the n, x to the 2n. This is our power series for 1 over 1 plus x squared. But that's not really what we are interested in. We want to find tangent. So in order to get tangent from this thing, we'd integrate it. So our f of x, which is equal to tangent inverse x, is equal to the integral of f prime of x, which is the integral of 1 over 1 plus x squared, which is going to be the integral of our sum, n equals 0 to infinity of -1 to the n, x to the 2n. Okay, so we're going to integrate this thing here. The integral of our sum, so that is tangent inverse x, is going to be equal to c plus, because again we're integrating, we're technically shifting it to the left, but in order to avoid the n equals -1 concept, we are just going to start at c, because that n to the -1 wouldn't really work out for us. So we'll just call it constant integration plus the sum, n equals 0 to infinity. Our constant stays the same, -1 to the n. We're going to take our x to the 2n plus 1. So that is, we're going to take our power, add by 1, and then divide by that new power, 2n plus 1. So that is our power series describing tangent inverse. And we can find c from here by just plugging in 0 for tangent inverse. So if we take a look, tangent inverse of 0 is 0. So again, c is tangent inverse of when x is 0, which is 0. So we end up with just the sum, n equals 0 to infinity, of -1 to the n, x to the 2n plus 1, all divided by 2n plus 1. This is our power series. And we can find our interval of convergence if we look here. Again, this -x squared here. -x squared is less than 1. Okay, so if we look at this thing, obviously the negative doesn't matter inside the absolute value. Now we would take the square root of both sides, and we would get the absolute value of x is less than 1. So that means our interval is from -1 to 1. But again, we're integrating this thing, so we actually don't know if these endpoints are included, but we at least know that the radius of convergence here is 1. Okay, so we can test these values if we'd like. If we plug in -1 and 1 in for x, we can get this and try it out. So let's go ahead and copy this down here, and we're going to test those endpoints. So when x is, we're going to start with -1. When x is -1, we have the sum n equals 0 to infinity of -1 to the n times -1 to the 2n plus 1 over 2n plus 1. All right, so these both have the same base, so we can add them. So we have 2n plus 1 plus n. That's going to be -1 to the 3n plus 1 over 2n plus 1. Now, if we think about this, when n is like, say, 1, 3 times 1 is 3, plus 1 is going to be 4. When n is 2, 3 times 2 is going to be 6, plus 1 is 7. So that would be an odd. The previous one was an even. Again, 3 plus 1, 4. So if we then go 3 times 3, that's 9 plus 1, even. So we have essentially our first one, 3 times, or I should have started at 0, I guess. 3 times 0 is going to be 0 plus 1 is 1, so that's odd. Okay. Then 3 times 1 is going to be 3 plus 1, that's even. Okay. So that is to say, if it's odd, -1, even, it's 1. Okay. I'm just making sure that this is in fact an alternating. Okay. So now the next one, when n is 2, 3 times 2 is 6, plus 1, odd. That's -1. We'll do one more. 3 times 3 is 6, or excuse me, is 9, plus 1 is 10. That's going to be even. So it's still alternating. So even though it maybe doesn't look it, it's still alternating. So really, this is like saying -1 to the n plus 1, since we're starting at 0, over 2n plus 1, something like this. Okay, so again, our first term here, 0 plus 1, that's 1. It's going to be odd. Okay, so that's what we're really dealing with here, is just an alternating series. So because it's a nice alternating series, all we have to do is check, does the limit as n approach infinity is of 1 over 2n plus 1, does this go to 0? Yes, it does. So we're doing the alternating series test. Now we just have to show that b sub n plus 1 is less than b sub n. So that is to say 1 over 2 times n plus 1 is less than 1 over 2 sub n plus 1. Okay, this would be 1 over 2n. I said 2 sub n plus 1 plus 1. I meant 2n plus 1 plus 1. That would be 2n plus 2 plus 1 is plus 3. That is definitely less than 1 over 2n plus 1. So that also checks. So it converges at -1. So we can include -1 here. Now we're going to try 1 next. Okay, so with 1, we're going to look back to this thing. If x is 1 here, we have -1 to the n times 1 to the 2n plus 1 over 2n plus 1. Well, this is meaningless. 1 to any power is just itself. And we're back to this -1 to the n, 2n plus 1, which we've already shown converges. So this also includes 1. So this is our interval of convergence. All right. Now, let's check out with our interval of convergence, -1 to 1. Let's see whether this series here, which is equal to our tangent inverse x, okay, let's go ahead and see whether our graph would agree with us. So let's first write out the first couple terms in our series. So our first term, when n is 0, that would be x over 1, okay, minus, when n is 1, 2 plus 1 is 3, 2 plus 1 is 3, plus x, when n is 2, 4 plus 1 is 5 over 5, minus x to the 7th over 7, plus x to the 9th over 9. Okay, so let's go ahead and see whether or not we agree with this thing. So in this case, it is still from -1 to 1. Technically speaking, I need to include them if I'm talking about this, but who cares? We'll get the picture. Okay, so here's our function. And we're trying to match this thing with our... So first off, x. Well, I mean, that's pretty decent already. So minus x cubed over 3. I mean, right there, I think we can really see that that's super obvious. Only on the second partial sum, plus x to the 5th over 5. I mean, that's even better. So it's pretty clear that this is definitely the same. All right. Let's take a look at another one. Find a power series representation for the function and determine the interval of convergence. Okay, so we have x over 1 plus 4x squared. All right, so in this case, we might say, ooh, this is not very close to our 1 over 1 plus, or 1 minus something. But it's moderately close. It's not super close, but it's kind of similar to what we've already done, where if things aren't exactly the same, we just make them the same through multiplying by constants or x's or whatever we need. Okay, so let's think about this real fast. If we were to simplify this a little bit, basically our f of x is like saying x times 1 over 1 plus 4x squared. And then this is at least a little bit better towards what we're kind of looking for. So if we think about this one, again, ignoring the power here, if we call 1 over 1 plus 4x, something like that, well, we could write a power series for that one. This would be 1 over 1 minus negative 4x. All right, so writing this as a power series, this would be n equals 0 to infinity of negative 4x to the n, which would mean that we have the sum, n equals 0 to infinity, of negative, we could call this like negative 4 to the n, x to the n. If it's a constant and it's alternating, we can just combine the alternating with the constant if we'd like. It doesn't actually matter. You could also write this as negative 1 to the n, 4 to the n, x to the n, but this is probably a little bit nicer looking. Okay, so this is what we have as this thing. Now clearly this thing is not the same here, but maybe we can get it there by taking the derivative. So let's think about it. If we have d dx of our 1 plus 4x to the negative 1, then that will be negative 1 times 1 plus 4x to the negative 2 times 4. So that is to say it is negative 4 times 1 over 1 plus 4x squared. Something like that. All right, so that's what this thing is. Now if you look, that's pretty close to these things. This thing is similar to this, but not quite right. So what we want to think about is like, how do we make this thing into this? Okay, so again, this thing is the derivative of that, and we want to make it into this. So first of all, this portion is good, but we need to, this one doesn't have a negative 4, so basically what we need to do is we need to take this thing here. Okay, so that is the derivative of d, well, rather than writing out the derivative, let's just write that thing. If we take this negative 4 times 1 over 1 plus 4x squared, okay, this is what we're trying to turn into this thing. So we want to make it equal to x times 1 over 1 plus 4x squared. Okay, so what we need to do to it is we need to kind of cancel out this negative 4. So how we do that is with a negative 4 here. So negative 4 and negative 4 would then make this thing equal to this thing as far as the constants and the signs. But we also need an x here, because x multiplied by this thing would then give us that. Okay. Now we're not doing things to both sides because we're not like solving an equation here. What we're just trying to do is, what would we need to do to our power series that we've kind of written out, well, in this case, our derivative, which we can then write as a power series, how can we make it into what we want it to be? And basically, all we need is an x and a -4. So the x to give it the x that this one has, and dividing by -4 to get rid of this -4 here, so it goes to a +1. All right, so that tells us then that x over 1 over 1 plus 4x squared is equal to x over -4 times this thing. But what is this thing? This thing here is the derivative of this, which would be the derivative of this. So times d dx of our power series, n equals 0 to infinity, of -4 to the n, x to the n. Okay, so we're going to do a little bit of cleanup work here. So first of all, we're going to derive this thing. So we still have our x and our -4 outside. When we take the derivative, n equals 1 to infinity. It's -4 to the n, and then we have n, x to the n minus 1. Okay, now we're going to put this -4 into this thing. Because we have this -4, it's in here on the bottom, so it's like we're dividing, so we subtract this. So when basically we have this -4 to the n over -4 to the 1, so that would be a -4 to the n minus 1. Okay, we're subtracting the powers since it's dividing. N equals 1 to infinity. This would be -4 to the n minus 1. We still have our n. X times x to the n minus 1. This is like an x to the 1. So we're adding 1 to this thing. So that would be x to the n. Okay, now as a final step, we could also, if we would like, rewrite this as n equals 0. So this is the sum, n equals 0 to infinity of -4. So when we subtract 1 from here, we need to add 1 to the other ends. So that's going to be n plus 1, x to the n plus 1. Okay, so that is our power series for our x over 1 plus 4x squared. That's what this thing is. And again, we'll double check that in just a sec, but let's first talk about our interval of convergence. Going back to this thing here, -4x is going to be our ratio. So we have -4x, absolute value less than 1. So that means that we have 4x is less than 1. So that means that absolute value of x is less than 1/4. So that means our interval of convergence is from -1/4 to 1/4. Okay, so we have our interval of convergence. So we are saying that this thing here, these are equal on the interval from -1/4 to 1/4. So let's go ahead and check that out. So -1/4 to 1/4. Did it again. Oh my gosh. There we go. Jeez. I just kept hitting shift at the same time somehow. Okay, so we have x over 1 plus 4x squared. Okay. All right, so this is what we're trying to mimic here with our series. Let's go ahead and think what our first couple terms are. When n is 0, this is a 1, x. So it's just x. Minus, when n is 1, we would have a -4 times 2 times x squared. I'm sorry, I wrote the negative twice. There we go. So it's a -4 here because of that minus. Plus, so this would be 4 squared times 3 times x cubed minus 4 cubed times 4 times x to the 4th plus 4 to the 4th times 5 times x to the 5th, etc. So let's take a look at it. We have x minus 4 times 2 times x squared. That's already looking okay. 4 squared times 3 times x cubed minus our 4 cubed times 4 times x to the fourth, and so on and so forth. I think we can agree that that's looking pretty good. Okay, so that's a good check. All right. So again, it doesn't really matter if this isn't in perfect form because we can force it into the form we need it to be. That's just something we need to keep in mind, is that we're using kind of the same logic we've done before with our derivatives. So it's just kind of making sure that we're keeping straight what we're doing. I think it's really easy for us to fall into steps of algebra where it's like, oh, this is a -4, so I'm going to divide by 4 over here or something and cancel it out. I mean, you could definitely think about it that way if you wanted, but I tend to think, okay, I'm trying to take this and I'm trying to match it to this. What do I need to do to this to match it to it? That's just how I keep it straight. Anyway, let's take a look at another one. So basically, one of the things that one of the reasons for this, obviously, has been that when we're taking the integral, or maybe not so obviously, when we're taking the integral of these things, sometimes we just don't know how to integrate stuff. That's one of the reasons we're doing this. I mean, if we look back at something like this, I haven't a clue how to integrate this thing as is. I mean, if I distribute it, then maybe I could because we have an x and we'd have an x squared. If we're talking about something like this, this could be like a u sub to integrate. But if I'm integrating like ln 5 minus x, I have no idea how to integrate that. I don't know the rule for it. And so instead, what we do is we write it as a power series. So ln here is as a power series, and then we could just integrate that thing if we needed to. The integral of this thing here, if we look back at this thing, the integral of this just follows the same rule of integration. This would, if we integrated this thing, it would be x to the n plus 2 over 5n plus 1, n plus 1, n plus 2. So again, we would just increase power, divide, and leave our constants the same. And then obviously integrating this thing as well, the integral of ln 5 would be ln 5x, and we'd also have to have a c constant of integration again. But basically, we could easily integrate this as a power series, but I don't know how to integrate ln off the top of my head. And so basically the idea is that in a lot of situations, what we're doing is we are integrating, or we're writing power series because we don't know how to integrate something. That's a very common reason for it. So we have some function which we can describe, but we can't describe the integral of that function. Sometimes because the integral of some function that is an elementary equation is not the integral of it is not an elementary equation, but it does exist. We can at least agree it exists. We just don't know how to write it. And so we write that thing as a power series instead. So let's say we're trying to integrate this thing. Now, I have no idea how to integrate something that is x over 1 minus x to the 8th. No idea how to do that. So what we need to do is we need to write it as a power series first. So if we're going to take this integral, we need to write this as a power series to be able to do that because I don't have any idea how to integrate this thing. Okay, so let's start by writing it as a power series. Well, if we have x over 1 minus x to the 8th, okay, well, that's like saying x times 1 over 1 minus x to the 8th, which is going to be x times the sum n equals 0 to infinity of x to the 8 to the n, which is x to the 8n. Okay? So that means that our sum, so that is x over 1 plus x to the 8th, this is equal to the sum n equals 0 to infinity. If we multiply x into here, we get x to the 8n plus 1. That's what these two things are. Okay? And again, we can quickly double check that thing. Let's talk about the interval of convergence here. That is when our x to the 8 is less than 1. So that is, it's between -1 and 1. Okay. So that's good because our interval of convergence is within the range that we're looking at this integral. Because like we can't use the power series for finding things outside of our integral. or outside of our interval, excuse me, of convergence. So this 0 to 1/2 is within our range, so we're good there. Let's just double check that everything's okay. So 1 to 1. All right, we have 1 minus x to the 8th, something like that. All right, that's what our curve looks like. And if we think about this in terms, so when n is 0, we'd have x. When n is 1, we'd have x to the 9th. I mean, already we can see that's pretty darn close. Okay. And of course it's red, so whatever. All right, so we're good here. This is going to work out for us. So we want to now integrate this thing. So if we're trying to find the integral of x over 1 minus, oh, I said a plus here when I wrote this. I did type it correctly here, though. Okay. Otherwise, I'd have to double check my graph. All right, so minus. All right, so we're saying that this is equal to this. So that means that the integral from 0 to 1/2 is equal to this same integral, as long as it's within our interval of convergence. So that's equal to the integral from 0 to 1/2 of our sum, n equals 0 to infinity of x to the 8n plus 1. So if we're integrating this thing, again, we have no idea how to integrate that, but we can integrate this thing. So that would be our sum, n equals 0 to infinity of, first of all, we have a constant of integration, though it's definite integral, so it doesn't actually matter, but it's still worth mentioning this. C plus, because we're integrating, we shifted it actually to the left, but to account for it, we just write C. And we have our n equals 0 to infinity. This is going to be x to the 8n plus 1, which would be plus 2, divided by 8n plus 2. This is our thing. And we're taking this from 1/2 to 0 by the fundamental theorem of calculus. Okay, so what does that look like? What does that mean for us? Well, basically, we have a power series of, again, the constants don't matter because they cancel out. We'd have this one, sum n equals 0 to infinity of 1/2 to the 8n plus 2 over 8n plus 2. That's what we have here. And we'd minus the sum n equals 0 to infinity of, plugging in 0 here, 0 to the 8n plus 2 over 8n plus 2. Now, if you think about this, 0 into this, that's 0. So really, we just have this thing, the sum n equals 0 to infinity of 1/2 to the 8n plus 2 over 8n plus 2. Okay. So if we think about this thing here, and we want to like integrate this thing. Now, in something like this, this thing will converge. I mean, that's one of the things that we're requiring of it, basically, is that this thing will converge. We can actually see that with the fact that this ratio here, this thing here is less than 1. I mean, that's basically what we're doing anyway. So this is going to converge to it. But, you know, we don't really have to use this as a convergence necessarily, as far as like, we don't have to find exactly what it is. We can, again, go back to our methods that we were doing before, where essentially we're finding a partial sum and seeing if it's exact enough for us. So if we're, say, doing this to some value, we only have to do it as accurate as we need, and we can make it more accurate by taking our n further. So if we take a look at this, let's just see what we can see. If n equals 0 to, let's say, 10, let's do the 10th partial sum first. This would be 1 over 2 to the 8n plus 2. Okay, over 8n plus 2. All right, so 0.125097, blah, blah, blah. So at 10, it's that. Let's see at 100. Okay, it hasn't changed. I mean, shoot, if we look at 5, compare this, let's copy this, and compare it to like 10. I mean, we can't tell the difference at 5. Let's see when we can tell the difference. Fourth partial sum? Nope. Third partial sum? There we go. That's the first time we can tell the difference. The third partial sum is only off by that. So, I mean, realistically speaking, we can be pretty exact with a very small partial sum in this one, and it's because this 8n plus 2. And so, basically, our 10th partial sum is overkill. Our third partial sum, if we wanted to go out further than our calculator goes, then we'd just take it to the fourth partial sum. So, essentially, this is approximately equal to, and I mean, it's as accurate as we can get right now on our calculator. This is equal to 0.1250978687752. That's as exact as we can be, and it was only needing the fourth partial sum to do that. So, again, that is the idea. So we're combining everything that we know now. We're integrating stuff, we're approximating our sum, etc. All right, let's do one more. Use a power series to approximate the definite integral here. Okay, so we're from 0 to 0.2. We have x to the 5th over 1 plus x cubed. Okay. So, first of all, this isn't really a good form for us. If we pull out the x to the 5th, that'd be 1 over 1 plus x cubed. That's almost a good form for us. That would be, I'm going to make some room. That would be x to the 5th times 1 over 1 minus negative x cubed. Now we're good. Now we can write this as x to the 5th times the sum n equals 0 to infinity of negative x to the 3rd to the n. X to the 3rd to the n, which is going to be an alternating series. N equals 0 to infinity. So that's negative 1 to the n, x to the 3n. That's what we have here. Now, we can combine that 5 into here. So that is to say, we end up with the sum n equals 0 to infinity of negative 1 to the n, x to the 3n plus 5. All right, so this is what our x to the 5th over 1 plus x cubed is. So all we have to do then is integrate it. Integral here from 0 to 0.2. But we have to double check. What's our radius of convergence, our interval of convergence specifically for us? If we take a look at negative x to the 3rd is less than 1, our interval is from negative 1 to 1. Okay, so we're okay here. So we're going to go ahead and integrate this thing. We end up with the integral of this is going to be the sum. C plus, the C doesn't matter with a definite integral, but I'm still going to write it. C plus the sum of negative 1 to the n, that stays the same, it's a constant, and we're going to take x to the 3n plus 6, we're adding 1 to here and dividing by that new power 3n plus 6. Okay, and we're going to take this from 0.2 to 0. Okay, so that means that for us the c's are going to drop off, but we're essentially having the sum n equals 0 to infinity of negative 1 to the n, 0.2 to the 3n plus 6 over 3n plus 6. We're subtracting the sum n equals 0 to infinity of negative 1 to the n. We're plugging in 0 for x here, so 0 to the 3n plus 6, terrible 3, over 3n plus 6. Now, same thing as before with this 0 here, it's always going to be 0. So when n is 0, that'd be 0 to the 6, it's 0, so that's just 0. So we're really looking at this thing here. So if we want to approximate this, all we have to do is do a partial sum. And we can approximate it as much as we want. Again, same thing as before. I didn't tell you what to approximate it to in this case because I don't really care about that right now. We're just talking about approximation. We're going to look at and see how good we could get with a few things. So we have -1 to the n times 0.2 to the 3n plus 6. And we're going to do over 3n plus 6. Okay? So at 4, this is what our partial sum is. At 5, it's pretty similar. 6, let's go 10. All right, that's pretty good. I mean, 0.0, so 1061011694111 versus 6941 here. Okay. So again, we can get more and more accurate as we take this thing out. So if we were to do it at 100, it doesn't change it to 10. So 10 and 100 is no better. So at our 10th partial sum, that's about as good as we're going to get on our calculator. So, well, it's as good as we're going to get on Desmos at least. So that's fine. 0.000010610116941. That is what this thing is. All right. So that is our kind of one of the reasons for writing things as a power series, is because we want to integrate stuff that maybe we don't have a clue how to integrate otherwise. And so we just turn it into a power series and integrate it. So that has been our representations of functions as power series. And I know it's a lot, but I wanted to do a lot of examples so that you can see it, because the more examples and the more times you do this, the easier it gets. Initially, it's super overwhelming. I understand that. I know as a student, power series is like, what? I don't understand. But the more you see it, the more you do it, the more practice you get with it. It really isn't too bad once you understand what it is that you're doing and for what purposes. So hopefully that helps you understand it better. Thanks for watching.